Okay, today we're going to talk about circular motion. In particular, we're going to focus on uniform circular motion, which is a constant rotation at a constant speed. So constant speed, but not constant velocity. And let's see that. So if we're a molecule or some other particle rotating here at a constant rate, at this position, we're heading in this direction with this particular velocity. And remember, the velocity is then the speed and the direction. And so there's that direction with that speed. But as we rotate, now a little bit later in the cycle, we're right here, and our speed is the same, but our velocity is in the other direction, or not in the other direction, but in the downward direction in this case. And so going back to Newton's laws, Newton's first law in particular, a body will remain in constant uniform motion unless acted on by a force. And if there's a force, then there's going to be an acceleration. And in order to bend this around, to change this direction, we have to have a directly inward pointing acceleration right to the center of the rotation. So that A is always pointing to the center of the rotation. All right, well, now let's consider a very, very minor, say infinitesimally small rotation. Then, for all practical purposes, this arc can be treated as a straight line. And so we can draw a triangle with, if we call this the radius, we make a small change in angle, and we can make a triangle with angle d theta, and this side angle d, or length dr. Now let's think about what happens to this vector. This vector also turns, and so we've turned here now by the same angle, because this is directly all the time the velocity is perpendicular to the radius. So if the radius changes a little, the velocity is locked to that. And so if this changes by this angle, this will change by that very same angle. And so this is the very same theta. Now these lengths might be different, right? Because the length is going to be a speed, and here it's a position. But the triangles will be similar. So we'll have similar triangles. And then from the geometry of similar triangles, we can show that this side ratio is equal. Okay. All right, so that's looking at the infinitesimal change. But also, what is dr? Dr is just the speed times dt, right? That's the rate of change, the small infinitesimal rate of change of r, well, not rate of change, but change in r, will be given to us by the speed times the change in time, this infinitesimal amount of time it takes to rotate that small amount. So we can set this also equal to rearranging here. We get d, so here's the r. So this is this, and then this r is here, and then this dr is this. So this dr goes right there, and this dr is this dr, and gets substituted in. This r is this r. Okay? These are magnitudes of these vectors. All right, well, what can we do here? Let's bring this dt over. We'll bring this v magnitude of velocity upward. That's dv dt. Well, that's the magnitude of the acceleration. And so we see that the magnitude of the acceleration is equal to the magnitude of the velocity squared divided by the magnitude of the position vector. Well, let's simplify so we don't have to draw as much. So we'll let A be the magnitude of the acceleration vector, V be the speed, right? Magnitude of the velocity, and r be the magnitude of the position vector. So with that, then we get our formula for centripetal acceleration. So this is centripetal acceleration. We saw this a little bit. We had to use it ahead of sort of working through this when we were looking at the solar system model of the hydrogen atom. And we just used it. But here we see where this comes from. We can derive it in this fashion. Now, we can, and often sometimes you'll see this, is we could call that a vector if we include a direction, and the direction would be directed inward. So you'll sometimes see that. Right? So we can either talk about it as a magnitude expression. If we give it a magnitude and the direction directed inward, then we can think of that as a vector equation. And then r would be the displacement vector at that point. But we will just use it as we had it, and we will see now the magnitude of the acceleration proportional to speed squared and inversely proportional to the size of the object that's rotating. So the faster we rotate it, the more acceleration, the more centripetal acceleration, and then the larger the object, the less centripetal acceleration. All right, well, again, as we used back with the hydrogen solar system model, if there's an acceleration and the object has mass, then we have force via Newton's second law, F equals ma. So F equals ma, since mass is a scalar, then the force must be in the same direction as the acceleration. Mass is not a tensor, so the force is in the same direction as the acceleration, so that means directed inward. We can write the magnitude equation as F equals m this A, and then we get the formula for centripetal force. Centripetal force. Okay, well, there's a related force that is an apparent force. It's sort of less fundamental than the centripetal force. But we know from Newton's third law, if there's a force, there's going to be a reactive force, right? And it'll be in the opposite direction. So what's that force pointing outward then? What's the reactive force pointing outward? That's referred to as centrifugal force. And just as a quick example, it's the basis for a centrifuge. That's where that word comes from. So let's imagine a little particle on a test tube. This is a test tube here, and it's being spun in a centrifuge. And this particle is up against the edge of the test tube. Well, the test tube is exerting a normal force on the particle and causing it to move inward. And so this is exerting the centripetal force on that particle. Now, the reactive force is that this particle is then exerting a force on the back end of that test tube. And that reactive force is called the centrifugal force. We'll label a little f here. Not a bad, it's kind of a bad letter, but at least for this lecture, we'll just call it little f. And that's the centripetal force. And it's equal and opposite that's the centrifugal force. I might have said centripetal. It's a centrifugal force. It's equal and opposite the centripetal force. And again, the origin of this is the third law. So how does it work in a centrifuge? Well, if we've got this distribution of particles, they're going to experience this centrifugal force. So the centripetal force is turning this test tube inward, and these will press against with their reactive force, and if it's just the solution, then they'll move through that solution. But then eventually they'll hit the edge of the test tube. And they do so in a way that's somewhat ordered. The heavier particles will push more and end up towards the top of this test tube, or bottom, however you're looking at it. And then, so if we pull the test tube out of the centrifuge, the heavier stuff will be at the bottom and the lighter stuff will be at the top. And that allows for separation. So centrifuges are good for separating parts of cells if they're just a regular centrifuge. And if they're ultracentrifuge, then you can actually separate proteins themselves based on mass and sometimes the shape too. All right, let's just pick up one last quick thing, and that is oftentimes when we're talking about a rotation, we talk in the language of period or frequency. So the period is the time for one rotation, and the frequency is just 1 over the period. So period, the units of period would be seconds, for example. The units of frequency would be 1 over seconds or hertz. And so that's frequency. Now the velocity is related to the period as well. So we know that the circumference is 2 pi r, and then how it goes that distance 2 pi r in what amount of time? Well, in the period. So 2 pi r over the period is the velocity. Now we can stick it back into this equation. We have the velocity, we have the position, and so we can take this and place it into this equation. And so we're going to get 4, that's the 2 squared, pi squared. Then we're going to get an r squared, and then a t squared. But there's an r already in this equation. So this r below will cancel the power there and reduce it to just r. And we're left here with 4 pi r over t squared for the relationship between the acceleration and the period. All right, so this is our first discussion here now of circular motion.